Astronomers in Durham have made the biggest ever computer model of the evolution of the universe, tracing its journey from the Big Bang to the present day. Meanwhile, in the heart of NASA's most advanced research facility, a machine that defies the limits of classical computation has just experienced something so mind-bending, so unprecedented, that NASA had no choice but to shut it down. Imagine a world where reality itself hangs in the balance, a world where the cutting-edge technology we rely on becomes a gateway to the unimaginable. What happened behind those closed doors? What did NASA's quantum computer discover that forced them to pull the plug? Join us as we unravel the mysteries of NASA's quantum shutdown, exploring the very edges of human knowledge and venturing into realms where science fiction meets reality. Quantum computers are like the rock stars of the tech world, grooving to the beat of quantum mechanics instead of the usual computer rhythm. Unlike regular computers that juggle bits as zeros or ones, quantum computers have unique elements called qubits. These qubits can exist in both 0 and 1 states simultaneously, thanks to a mind-bending phenomenon called superposition. This allows them to multitask at an extraordinary level, performing complex calculations all at once. Quantum computers are the rebels of technology, leveraging qubits' extraordinary abilities to process information in ways that defy traditional logic. While classical computers follow strict binary rules, quantum machines use superposition and entanglement, making them capable of juggling vast amounts of data simultaneously. To understand the roots of this quantum revolution, we must rewind to the early 1990s, when quantum theory began turning heads and sparking scientific breakthroughs. Quantum mechanics explores the fundamental building blocks of the universe, atoms and subatomic particles. In the 1920s, physicist Max Planck introduced the idea that energy is quantized, laying the foundation for quantum computing. Then, in 1925, Werner Heisenberg introduced the uncertainty principle, stating that it is impossible to determine both the exact position and momentum of a particle at the same time. This revelation shook the scientific world, proving that the quantum realm operates on probabilities rather than certainties. Fast forward to 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen introduced the EPR paradox, challenging the nature of quantum entanglement. By 1980, the concept of quantum computing emerged, promising mind-blowing computational power far beyond classical computers. In 1982, physicist Paul Benioff proposed that a computer could leverage quantum mechanics, suggesting that quantum machines could outpace traditional computers like race cars against bicycles. That same year, Richard Feynman, one of the greatest minds in physics, saw quantum computing as a revolutionary tool capable of solving problems that classical computers could never crack. His vision ignited a wave of excitement in the scientific community, paving the way for deeper research into the mysteries of quantum mechanics. In 1994, mathematician Peter Shor introduced an algorithm that demonstrated the true potential of quantum computers. Suddenly, these machines could solve complex problems at speeds unimaginable to classical systems. By 1998, researchers at Los Alamos National Laboratory had built a primitive quantum computer with just 2 qubits, using nuclear magnetic resonance technology. Though still in its infancy, this achievement marked a significant milestone in the development of quantum computing. As the 2000s unfolded, research accelerated, with laboratories and companies worldwide competing to refine and expand quantum capabilities. By 2021, IBM made history with its 127-qubit quantum processor, a leap forward in computational power. Scientists also developed quantum error correction techniques, shielding qubits from interference and making quantum systems more stable and reliable. In 2005, researchers at the University of Innsbruck and the National Institute of Standards and Technology created a 5-qubit quantum computer, proving that practical quantum computing was within reach. 2 years later, in 2007, Yale University scientists developed more stable qubits using solid-state materials, making quantum computers more manageable and commercially viable. The breakthroughs didn't stop there. In 2010, the University of Science and Technology of China achieved a mind-blowing feat: quantum teleportation. Although not teleporting people, they successfully transmitted quantum information across a staggering 10 miles, opening doors to the possibility of large-scale quantum networks. This groundbreaking experiment demonstrated that quantum information could travel vast distances without physical transfer, revolutionizing the future of communication and cryptography. By 2013, Google and NASA joined forces to create the D-Wave 2, an advanced quantum computer designed for artificial intelligence research. However, an unexpected government shutdown disrupted the project, causing delays and financial setbacks. Restarting such a machine was no small task. It required enormous resources and precision. Meanwhile, Google faced its own challenges, having heavily invested in quantum AI, betting on its ability to outperform classical computing. Quantum computing continues to reshape our understanding of reality, pushing the boundaries of human knowledge. As scientists unlock the secrets of the quantum realm, we stand at the precipice of a new technological era, one where quantum machines might hold the answers to some of the universe's deepest mysteries. The future of computing, artificial intelligence, and even space exploration may hinge on our ability to harness the full power of quantum mechanics. The journey has only just begun. Astronomers in Durham have created the most extensive computer model of the universe's evolution, spanning from the Big Bang to the present day. Meanwhile, inside NASA's most advanced research facility, an extraordinary event occurred. A machine that defies the limits of classical computation experienced something so unprecedented that NASA had no choice but to shut it down. Imagine a world where reality itself is on the verge of transformation, where cutting-edge technology becomes a gateway to the unimaginable. What happened behind those closed doors? What did NASA's quantum computer uncover that forced them to pull the plug? Join us as we unravel the mysteries of NASA's quantum shutdown, venturing into the realms where science fiction meets reality. Quantum computers are like the rock stars of the tech world, dancing to the rhythm of quantum mechanics rather than the predictable beats of traditional computers. Unlike conventional computers, which process information as zeros and ones, quantum computers use qubits, mysterious entities that can exist in multiple states simultaneously due to a phenomenon called superposition. These qubits allow quantum computers to perform incredibly complex calculations at speeds that leave classical machines in the dust. They are the rebels of the computing world, leveraging quantum entanglement and superposition to process information in ways that seem almost magical. To understand how this quantum revolution began, we must rewind to the early 1990s when quantum theory took center stage, reshaping our understanding of reality. Quantum mechanics delves into the fundamental building blocks of the universe, atoms and subatomic particles. Back in the early 20th century, Max Planck introduced the radical idea that energy comes in discrete packets, which later became the foundation of quantum computing. In 1925, Werner Heisenberg introduced the uncertainty principle, stating that it is impossible to precisely determine both the position and momentum of a particle simultaneously. This principle highlighted the bizarre nature of the quantum world, filled with probabilities rather than certainties. Fast forward to 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen introduced the EPR paradox, challenging the strange concept of quantum entanglement. Decades later, in 1980, the idea of quantum computing took shape, promising to harness quantum mechanics for groundbreaking computations. Physicist Paul Benioff envisioned a computer that utilized quantum principles, a concept further developed by Richard Feynman, who saw quantum computers as the future of computation. In 1994, mathematician Peter Shor created an algorithm that could break modern cryptographic codes, showcasing the true potential of quantum machines. The journey of quantum computing gained momentum in 1998 when scientists at Los Alamos National Laboratory built a 2-qubit quantum computer using nuclear magnetic resonance techniques. By the early 2000s, research into quantum computing exploded, with IBM, Google, and other tech giants racing to develop more powerful machines. In 2021, IBM unveiled the IBM Qubit, a 7-qubit quantum computer that marked a major milestone in quantum technology. Researchers also developed quantum error correction methods, creating robust systems to protect quantum information from environmental disturbances. In 2005, scientists at the University of Innsbruck and the National Institute of Standards and Technology built a 5-qubit quantum computer, demonstrating that practical quantum machines were within reach. By 2007, Yale University researchers created more stable qubits using solid-state materials, making quantum computers more viable. A major breakthrough came in 2010 when the University of Science and Technology of China achieved quantum teleportation, transferring quantum information across a distance of 10 miles, an achievement that laid the foundation for quantum networks. In 2013, Google and NASA partnered to develop the D-Wave 2 quantum computer. However, an unexpected government shutdown temporarily halted the project, creating a major setback. When operations resumed, the D-Wave 2 was back in action, reigniting the excitement for quantum research. In 2019, Google made headlines by demonstrating quantum supremacy, proving that its quantum computer could solve problems that were practically impossible for classical machines. This breakthrough fueled competition, pushing IBM, Microsoft, and other tech giants to accelerate their quantum initiatives. By 2020, IBM launched the IBM Quantum System 1, the first commercial quantum computer, transforming quantum computing from a theoretical concept into a practical tool for businesses and governments. Recognizing its transformative potential, governments worldwide began investing heavily in quantum research, establishing cutting-edge laboratories to advance the technology. Meanwhile, an astonishing theory emerged in the scientific community. What if advanced alien civilizations were using black holes as supercomputers? This idea, rooted in the Fermi paradox, suggests that extraterrestrial beings might be harnessing the immense power of black holes for quantum computations. Since the 1960s, scientists have been searching for radio signals from intelligent life. But some researchers argue that we should expand our search to detect advanced quantum communication methods, such as neutrinos and gravitational waves. Physicists like Jan Valley and Zaza Osmanov have proposed that extraterrestrial civilizations could be using black holes as massive quantum processing hubs. These black holes, potentially engineered by hyperintelligent aliens, could emit intense radiation, including Hawking radiation, which might be detectable by observatories like IceCube in Antarctica. If this theory is correct, it could explain the absence of clear extraterrestrial signals. Perhaps these advanced civilizations communicate using methods far beyond our current understanding. As quantum computing advances, ethical concerns arise. Famed physicist Michio Kaku has warned that quantum technology could be misused for information control and manipulation. Governments might exploit quantum computers to monitor and censor information, creating a dystopian future where truth itself is dictated by powerful entities. Deepfakes, AI-generated misinformation, and biased algorithms already pose threats to society, and the rise of quantum AI could amplify these issues. Despite these concerns, scientists continue their quest to build the ultimate quantum computer, a challenge that could take years or even decades to overcome. Researchers are exploring two main approaches: gate-based quantum computing, which aims to control individual qubits for precise calculations, and adiabatic quantum computing, which gradually evolves quantum systems to solve complex problems. Achieving quantum coherence, maintaining stable qubit interactions, remains a significant hurdle, requiring ultra-cold, isolated environments. As the quantum revolution unfolds, humanity stands at the edge of a new era, where computation transcends classical limitations, unlocking mysteries that were once beyond our grasp. Whether quantum computers will usher in a utopian age of discovery or a dystopian future of control remains to be seen. But one thing is certain: this journey into the quantum realm is just beginning. Scientists are on a mission to figure out how to handle errors in quantum computing and make these machines more reliable. If mistakes sneak in, the results can go haywire. With quantum technology advancing rapidly, governments, schools, and major companies are jumping on the bandwagon, pouring massive funds into research and development. Tech giants like IBM Quantum, Google Quantum AI, and Microsoft Quantum are leading the charge, providing scientists with top-notch hardware, software, and all the knowledge they need. The fast-changing world of quantum computing continuously brings fresh ideas, innovative software, and new breakthroughs that push the limits of what's possible. Mission success rates skyrocket as quantum computing reshapes technology and security. Traditional encryption methods could become obsolete, as quantum attacks have the power to crack even the toughest codes. Quantum cryptography, using principles like entanglement and superposition, is emerging as the guardian of interstellar secrets, ensuring that no eavesdropping aliens or hackers can interfere. Beyond security, quantum tunneling could revolutionize space travel, turning quantum computers into efficient spacecraft engines that propel us through space like never before. These cutting-edge machines optimize logistics, craft new materials, and predict nuclear reactions, making them more than just tech marvels. They are the rock stars of the space age, pushing technology to its limits. Quantum sensors act as the super spies of the cosmos, detecting targets with surgical precision, while quantum communication functions as the ultimate secret agent hotline, ensuring real-time data analysis in high-stakes situations. In the grand theater of cosmic conflicts, quantum computing takes center stage, promising military mastery. However, lurking in the shadows are potential threats and challenges that demand our full attention. Encryption, the silent protector of digital security, faces an existential showdown. It safeguards everything from online banking to government secrets with mind-bending mathematical barriers. Classical computers struggle to break these codes, making encryption a digital fortress, but quantum computers could change the game entirely. Imagine if quantum computers fell into the wrong hands. Private financial records, classified intelligence, and even entire economic systems could be compromised. Cryptocurrencies like Bitcoin, which rely on secure cryptographic keys, might also be at risk. If quantum computers become powerful enough to crack these codes, the stability of digital currencies could be thrown into chaos, shaking trust in the online economy. To counter this threat, researchers worldwide are racing to develop post-quantum cryptography, an advanced form of encryption designed to withstand quantum attacks. This battle between quantum computing and cybersecurity is an unending clash, echoing through the digital realms as we strive to protect sensitive data from future threats. At the heart of the internet lies a delicate balance maintained by encryption, specifically public key cryptography, which secures communications, transactions, and data transfers. However, quantum computers have the potential to dismantle these encryption algorithms, leaving once secure fortresses vulnerable. This raises serious concerns about data privacy. With their immense computational power, quantum machines could unravel encrypted datasets, revealing hidden patterns and correlations. This cosmic challenge affects individuals and organizations alike, as they rely on encryption to safeguard personal information and trade secrets. The stakes are high, and the outcome remains uncertain. Will encryption stand strong against the quantum tide, or will we be forced into uncharted digital territory? Only time will tell. The need for strong regulations to protect sensitive information has never been more critical. Quantum computers introduce a new layer of complexity, potentially shaking the foundations of scientific simulations and models. Scientists and researchers face a daunting challenge. Quantum computers have the power to compromise the integrity of crucial simulations in fields like material science, drug discovery, and climate modeling. If encryption protecting these simulations is broken, unauthorized access to sensitive information becomes a real threat. To counteract this, cryptographers and cybersecurity experts are actively developing quantum-resistant encryption methods, also known as post-quantum cryptography. Their mission is clear. When quantum computers reach their full potential, our digital world must remain secure. Quantum technology is ushering in a new era of computing, and with it comes the need for stronger defenses against cyber threats. Governments, tech companies, and security experts are working together to create next-generation encryption techniques, building a digital shield to protect against the quantum revolution. Quantum computers are more than just powerful machines. They represent both promise and peril. While they offer revolutionary advancements in computing, security, and scientific discovery, they also introduce significant risks. Our online defenses must evolve to meet these new challenges. A global team of experts and researchers is tirelessly working to develop encryption methods strong enough to withstand quantum attacks, ensuring that our digital world remains safe. As we stand on the brink of a quantum-powered future, the race to secure our information is more crucial than ever. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more quality content.